This is James Grass, and this is my Lab 4 video report. In this lab, I used the principles of energy conservation and current conservation called the loop rule and charge conservation respectively. The loop rule states the sum of all electric potential differences around a loop is zero. The current conservation follows the law of conservation of energy. I will use these principles to predict the behavior of circuits containing restrictors in series and in parallel, examine the behavior of ohmatic resistors and capacitors, and use the multimeters to measure actual values of conventional current and potential difference in circuits. I predicted the current in I1 and I2. For I2 to be higher than I1, I said that I2 will be around 0.1 A and that I1 will be around 0.05 amps. My predictions were not right, as they were both equal and equal to 0.02 amps. Backwards, the current still read 0.02 amps. The readings on both of the two meters were 3 volts on the voltmeter and 0 on the ammeter. The new readings were because the wires were not connected, the current doesn't flow, so the ammeter read 0, but the voltmeter could read 3 volts because it was still touching both sides. Using the voltmeter to measure the potential difference around each part of the circuit, this is what I found, with the only ones reading above 0 were the FE portion, the DC portion, and the BA portion, which were the resistors and the batteries. The current across the entire circuit was 0.02 amps. The sum of the potential differences for round trip should be 0, and I measured it to be 0. Here is a graph of my data and observations. When I attached the voltmeter, I altered the circuit, but the ammeter didn't change because the voltmeter doesn't change the current. Once I placed the voltmeter parallel with the 100 ohm resistor, the current changed to 0.06 amps because the current follows the path of least resistance, so it travels along the path with the ammeter instead of flowing through the resistor. Here are my calculations for the potential difference of certain portions of the circuit, with both of the resistors calculating to roughly what they're supposed to be in theory, and the wire and ammeter having no resistance. The discrepancy for the resistors in their calculations is likely due to rounding in the calculations. The light slowly fades after initially lighting up once the battery is connected to the capacitor and bulb in series, and when it's disconnected, the current flows again, so it lights up and then fades off. When I first connected the battery, the capacitor was charging and the current was moving until the capacitor was charged and the current stopped flowing. When I removed the battery from the circuit, the same thing began to happen. I measured the time it took for the capacitor to charge and discharge with a 10 ohm bulb and a 20 ohm bulb, and here are the results. The 20 ohm bulb took a lot longer, which was expected. The interesting thing is that it takes longer to discharge than to charge. Here is the data for the next portion of the lab, where I took the voltage at certain stages of a circuit and plotted them based on the ln of the dV over V initial to get a linear plot. Here it was, and using the slope, I found the RC to be 6.2112, which is very close to the time at which the CCK showed the value to be 1 over E, what the initial voltage was. If I was doing this lab in real life, the real ammeter would have a low level of resistance. It would have changed the current value and affected the readings of other portions. And the same thing is applied to if there was no resistance in the circuit if it was just the capacitor and the battery, because the model predicts that it would charge instantly, but wires in real life have a low level of resistance, so it would be almost instant, but not exactly instant. And here are some images of my lab throughout the stages. And that is the end of my video lab report.